Well, even though chapter 18 is not going to be included in the final exam, I wanted to give you a sort of a superficial view of this, just in case in 228 you may need some of these concepts. So this chapter deals with, uh, oops, sorry. This chapter deals with ethers and epoxides. So let's have a look at this. Yeah, ethers and epoxides, and so in the early chapters of this semester, we learned that an ether is any structure where you have an alkyl group and you have an oxygen, and then you have another alkyl group, or you can have an alkyl group from one side and an aryl group from the other side. Anything goes. And so all those will be ethers. Then epoxide, it was a particular case of a cyclic ether where you have a small ring like this. We learn in chapter 7 that we can prepare epoxides by reaction of an alkene with metachloroperoxybenzoic acid. And then the other functional group we have, so this is epoxides. And then the other functional group we have is the thiols. And thiols is just the sulfur version of an alcohol. And so we are replacing oxygen with sulfur. That is a thiol. And then you have sulfides. Those will be the sulfur version of the ethers. And so you can have something like this. And you have a sulfur that is flanked by two alkyl groups. That will be a sulfide. By the way, thiols and sulfides, they tend to be very, very smelly, very stinky compounds. So here we have some examples of, we have an ether, we have diethyl ether. So we name, for the nomenclature, we name the nature of the alkyl group. This is an ethyl. The other is also an ethyl. So that's why we call it diethyl ether. You can have two different groups, like you can have a phenyl group and a methyl group. So in that case, we name alphabetizing. Methyl comes before phenyl, so it will be methyl phenyl ether. And then we have a special case here of a cyclic ether of a 5-member ring with an oxygen, and we call that tetrahydrofuran. We have already met that one in chapter 11. We learned that this is a very good solvent for running SN2 reactions. Then more examples of ethers. Here we have a case that you have an isopropyl group from one side and a methyl group from the other side. You alphabetize, isopropyl comes before methyl, isopropyl methyl ether. Some other examples are in which you, instead of using this terminology of alkyl ether, you can use the substituent here as being a methoxy. And because you have two methoxy groups and you have a phenyl ring, so you can name this as para-dimethoxybenzene. How can we prepare ethers? Well, there is one very cheap method for preparing ethers, but the method is rather limited. And this method implies protonation of the oxygen of the ether with a mineral acid, like a sulfuric acid. And that will transform your OH into a good living group, OH2 plus. It's a water molecule, a good living group. And then you can have another molecule of an alcohol that can act as a nucleophile in an SN2 reaction, and then you displace that water molecule. And then the product that you obtain will be essentially the protonated form of an ether. So all what is left to obtain the final product, it will be deprotonation of this protonated ether. You can use a water molecule as a base for the deprotonation. And then after deprotonation, you get the final product. Let's see another example. Let's say that I want to prepare this ether. So what I should use, it will be propyl alcohol, right? Propyl alcohol. Then I will get protonation of this with an acid. I can use an acid. Protonate this to form the good living group water. And then I can have another molecule of the same alcohol that can act as a nucleophile, displace the water molecule, and in that way I will form the dipropyl ether after the deprotonation of the oxygen, and that will give me that as a final product. As you can see, there is a limitation, and the limitation is that naturally the ethers that we can prepare will be only ethers that are symmetrical. So we cannot prepare unsymmetrical ethers using this methodology. Another method that is a little more general, and that will allow you to prepare non-symmetrical ethers, is the so-called Williamson ether synthesis. This is the method that was invented more than 150 years ago, and it's still used. It still works pretty well. So the idea in this method is that if you have an alcohol, you can use a base like a sodium hydride for deprotonation of the alcohol. Deprotonation because you have a hydride. Hydride is a good base, and in that way you can prepare the alkoxide. And then the alkoxide can act as a nucleophile reacting with an alkyl halide like methyl iodide. Nucleophilic substitution, displacement of the I minus, and the final product that you obtain will be the cyclopentyl methyl ether. Let's see another example. Let's say that the product that I want to make, it will be something like this. And so that will be propyl, that will be ethyl propyl ether. And that is my target product. How can I make that? Actually, I can make it in two different ways. I can use propyl alcohol. I react that with sodium hydride. That will allow me to make the alkoxide. And then I can react this alkoxide with the 2-carbon atom halide. I can use a bromide, for instance. And then I will have displacement of the bromide, and I will get the final product. Or the other method in which I can prepare this, it will be by reacting ethyl alcohol with sodium hydride. That will allow me to make the ethoxide. And then I can react the ethoxide with the corresponding propyl halide. Let's say I'm using 1-iodopropane, nucleophilic attack, displacement of the I minus, and that will give me the final product. So there you can see the method is quite general. There is a limitation in this method, and the limitation is that if you have two halves, let's say that one of the halves is more highly substituted. So I want to prepare something like this. I want to prepare this. So in principle, you will say, I can use terbutanol, deprotonate that with sodium hydride, and then react that alkoxide with the corresponding halide, right? So which one should be the halide that I need to use? Well, I will need to use something like a CH3Br, right? Nucleophilic attack, displacement of the Br minus, and I will get my final product. Yeah, in this case, it is true that that method will work quite well. But how about if I try to do it the other way around? And how about if I have the bad idea to say, yeah, I'm going to prepare the alkoxide out of methanol, deprotonation of that with sodium hydride, that will give me my alkoxide. So far, so good. But then now, this is the step that will not work really. Here I said, I'm going to use this particular halide. The problem here is that because this is an SN2 reaction, the approach of the base, the approach of the nucleophile to the central carbon atom will be too difficult. And instead of that, what will happen is that these hydrogens here, they are a lot more accessible, right? So rather than getting that as a final product, I will not get this as a final product. What will happen is that I will get a derailment here, and this is going to act as a base. It will abstract a proton. We will form a double bond, and the leaving group will depart. And surprise, surprise, rather than getting formation of the product that I wanted, I will get formation of this product. So instead of getting substitution, I will get elimination taking place. So that's why the recommendation here is that all the time for a successful Williamson ether synthesis, you should use the more highly substituted alkoxide with the less highly substituted alkyl halide. You see, here, the more highly substituted alkoxide is the terbutanol. I can deprotonate that and produce the alkoxide of the more highly substituted moiety. And then the product on which I will perform the substitution will be the less highly substituted alkyl halide, the 1-bromo, the bromomethane. I don't even need to put a name, a number here, because there is only one carbon atom. So in the next mini video, I will show you another alternative method for making ethers using a method that is inspired in the alkoxy mercuration.